Okay, so new chapter after the chapter on infinite series. This is the chapter 8 on infinite sets. So in this chapter we are going to primarily study cardinalities of sets which are infinite, and in fact if you recall, in the section 3.6, that is the last section of chapter 3, where we dealt with finite sets, in that section itself we in fact have already seen the definition of infinite sets. So we already know what infinite sets are. So let us just briefly recall that definition. First of all, we need to know what finite sets are. Say you have a set S, and say you come across a natural number, some natural number n, such that you find a bijective function from S into this set, the set of all natural numbers I, such that 1 is less than or equal to I and I is less than or equal to n. If it happens that there is such a bijective function f between S and a set which looks like this, then S is called finite, and this natural number n is, in that case, it is called the cardinality of S. And in fact we saw in some of the results in this section that the cardinality of S, once it exists like this, that is, if S is a finite set according to this definition, then its cardinality is a unique natural number. And we in fact devised this notation also to denote the cardinality of S. And a part of this definition says that if this does not happen, that is, if for a given set S, it turns out that there is no natural number n for which all these things happen, then S is said to be infinite. In other words, to put it more simply, if S is a set which is not finite, then it is defined to be infinite. Okay, so infinite just simply means not finite. And in this section itself, we came across one example of an infinite set which is just this, the set of natural numbers. We proved that this set itself is infinite. So in this section, and in fact in this chapter itself, we are going to see cardinalities of infinite sets. And regarding that, here is the first notion of countability. So this is the first section. So let us now see what the author has to say here. It starts off like this: from proposition 3, 6, 14 C, that means part C of this proposition. This is again coming from this section on finite sets. We know that if X is a finite set, and capital Y is a proper subset of X, then capital Y does not have equal cardinality with X. In fact, in this part of the proposition we find that in that case, when Y is a proper subset of X, then the cardinality of Y is strictly less than the cardinality of X. This is something that we proved when we studied these things. And Y is a proper subset of X, then Y does not have equal cardinality with X. That means this is a property of finite sets, which in general is true, that you have a set which is finite and you find a proper subset inside that set, finite set. Then the cardinality of the proper subset under no circumstance will be equal to the cardinality of the original larger set. However, this is not the case with infinite sets. So there a difference arises, and we are going to look at this difference first of all. However, in this very next line, however, this is not the case for infinite sets. For instance, and we are going to give an example of that thing. We know from a result which says that the set of natural numbers is infinite, and that result is theorem 3612. So all of these things, all of these results about finite sets are of course going to come from this section. We know from theorem 3612 that the set of natural numbers that is n is infinite, and so is the proper subset which is the one that you get from n by removing the natural number 0 from it. This proper subset is also infinite. And where is this thing coming from? See proposition first part of this proposition 3614. If I am yes, part A. Okay, but how and what is in fact 3614 part A? In that part we have this thing. in part A of that proposition, the statement is this. Say you have a finite set X, a finite set, okay, and say you have some object X, any object whatsoever, which is not an element of X, then the union of X with this singleton set consisting of that object is also finite, and its cardinality is equal to the cardinality of your X plus 1, of course a very natural looking thing, and which is true also. Okay, so but how are we using this fact to conclude that this must also be infinite, just like n? That is because if you suppose to the contrary that this is finite, then you can consider this thing in place of X. So if you are supposing that this is finite, then according to this result, this union must be finite. Note that 0 is an object which does not belong to this set, just like this one, this general result. That is, but this union is nothing but the set of natural numbers, so n should be finite, which would contradict theorem 3612. That's why this cannot be finite. This must also be infinite, just like n. In other words, what we feel should be true is indeed true. If you remove one element from an infinite set, and whatever is left, that is still infinite. Okay. However, but okay, so now what do we have? We have an infinite set n, and we have a proper subset of n which is also infinite. However, the function f from okay, so I am going to set up a correspondence between this and that one. Given by this formula is a bijection, and this is something which does not happen, it can never happen with a finite set. Whatever we wrote here, that if you have a finite set and a proper subset of that finite set, then there can be no bijection, no one-to-one correspondence, no one-to-one onto function between them. However, for this infinite set and this proper subset of that infinite set, we find that there indeed is a bijection. It may still be a little, you may be still a little doubtful about this, but you can of course prove that this function is indeed a bijection. Let me just quickly demonstrate that fact. So to see that it's a bijection, note that f is one-to-one because if say n1 and n2 are two natural numbers such that f of n1 is equal to f of n2, then that just simply means what? n1 plus 1 is equal to n2 plus 1, or n1 is equal to n2. That means for two elements in the domain of the function, if their outputs are equal, I mean the outputs of the function corresponding to those two inputs are equal, then the inputs must also be equal, which is just the condition for one-to-oneness. So that's why this function is one-to-one. Also, f is onto since for any y belonging to n minus 0, we have, so we should get an inverse image for this element under f. If we do, then that means every element of the second set, that is n minus 0, has an inverse image. So the function would be onto. So being one-to-one and onto, of course, it would then be a bijection, which is what we are claiming. We have y minus 1 belonging to n such that f of y minus 1 is equal to y minus 1 plus 1, so that means you would get y. So actually we have shown everything that one needs to show in order to make this claim that this is a bijection. But there is still one more issue which you may miss at first glance. The issue is of well-definedness. Keep in mind that well-definedness does not always mean showing that for a given input there is a unique output. Of course it's there, it should be there. But there is another thing which comes even before that. When you are taking an input, you should first of all make sure that the output belongs to the set. That is this second set. Now, if our n is a natural number, then naturally, no pun intended, n plus 1 is also a natural number. From the elementary properties of natural numbers, that is from the first piano axiom. So n plus 1 is a natural number, but is it possible for n plus 1 to ever be equal to 0? Because if that happens, then that is not there in this set. However, that is not possible since the smallest value that n can take is 0 itself, and in that case also this n plus 1 is 1. So this n plus 1 is never equal to 0, and in fact this is, I think, if I am remembering correctly, the third piano axiom. 0 is not the successor of any natural number. So that is why all the outputs are actually here in this set, and hence the function is well defined, but not mentioning those trivial things here. In fact, this itself also need not be mentioned, as it is something quite routine. Okay, so we now see a very stark difference between finite sets and infinite sets. I think it would be even better to see it as a diagram. In fact, you see, the set n of course has these elements 0, 1, 2, 3, etc. goes like that, and n minus 0 has these elements 1, 2, 3, 4, etc. So according to our function, we maps 0 onto 1, 1 onto 2, 2 onto 3, 3 onto 4, and so on. And in this diagrammatic form, you can immediately see that the function is a one-to-one correspondence, but that's just simply a guess. You have to actually verify it, which we have done. But another another even better thing is to in fact not just look at n minus 0 like this, but look at another n itself. That is, so here we have not done anything different than just simply restating the fact whatever we wrote there above in this pictorial form. But now watch this. So we are again considering another copy of n. So what we are doing is this, and this of course will be mapped onto 4. So this part is your n minus 0, which despite being a proper subset of n, because it does not have 0, has a one-to-one correspondence with n itself, and this is not possible inside a finite set, as we proved earlier. So this difference is there between finite sets and infinite sets. And regarding all these things, this in fact reminds me of something. It's called Hilbert's Hotel. David Hilbert's Infinite Hotel. It's like you have a hotel in which you have infinitely many rooms. What type of infinitely many rooms? As many rooms as you have natural numbers, say. So that means there is a room labeled 0, then there is a room labeled 1, room number 1, number 2, number 3, and so on. It just goes like that. And say the hotel is full. Each room has a guest, but still if someone else arrives, someone else shows up and wants to check in, then they can also be accommodated. What the guests will do, the guest who is in room number 0, they will relocate to 1. The guest in 1 will go to 2. The one in 2 will go to 3, and so on. So that one room will become vacant. It can then be used by the new guest. So that is the strange nature of infinity. In spite of being full, still more rooms can be created. And in fact, if infinitely many guests arrive, then also they can be still accommodated. In that case, what you have to do, you have to send 0 to say 2, 1 to, or say 0 to 1, 1 to 2, 2 to 4, 3 to 6, 4 to 8, 4 to 8, okay, 5 to 10. So that means you send the guest who is residing in room number n to room number 2n, so that infinitely many rooms now become vacant. Those rooms which are labeled with odd numbers, odd natural numbers. So such strange things happen when you encounter and when you deal with infinity. So this is the first strange thing. But infinity also is not just a, of course it's a notion, but you should not think that there is a single infinity or anything like that. There are there are in fact infinitely many different types of infinities. For every infinity there is a bigger one. So we are going to see those type of things. The smallest type of infinity looks like this, where the things are discrete but the counting never stops. And this is in fact one characteristic of infinite sets. This is not just simply just a property of n and this particular subset of n. In general, if you have any infinite set, there you will always obtain a proper subset with which it will have a one-to-one correspondence. In fact, it turns out that this property is equivalent to a set becoming infinite. Okay, so these two things are actually equivalent. If you have an infinite set, then there will be a proper subset with which it will have a one-to-one correspondence, and conversely, if you find such a proper subset of a set with which it has one-to-one correspondence, then it must be infinite. Okay, so that itself can be used as a definition of infinite sets because of this reason. So that's why the author writes, this is one characteristic of infinite sets. That means this property can be used to characterize infinite sets. And in this regard, see the first exercise. We will of course see when we solve the exercises. Okay, now it's time for us to distinguish between different types of infinities, and the first thing we are going to distinguish is we are going to call the smallest type of infinity something, and the rest, the other types of infinities, something else. And do not get confused when I keep saying things like infinity, the smallest type of infinity. For us, they are just cardinalities of these sets. Of course, because our sets are infinite, we are not attaching any object to the cardinality. It's just the infinitude of the set, the infinite size of the set. For example, what I'm trying to say here is that just like when you had a finite set X in your section 3.6, there the finiteness was measured by natural numbers. That is, the cardinalities were measured by natural numbers. This turned out to be a natural number which was associated with a set and it becomes its cardinality. Here, however, we are not doing anything like that. It can be done, but we are not doing anything like that. Some such symbols can be devised for these infinite sizes also. Okay, so here comes the first definition. And this is the definition of countable sets here. And the definition goes like this: a set X is said to be countably infinite or just countable if it has the same cardinality as the set of natural numbers. As the set of natural numbers. So what does this say? It says that a set X is said to be countably infinite or just simply countable if it has the same cardinality as n. That means if there exists a bijective map from X to n or from n to X, if one of them is true, then the other is also true, because you can consider the inverse map. Okay, so this is one thing. A set X is said to be at most countable if it is either finite or countable. That means an at most countable set is either infinite, in which case it is countable, that is it has a bijection with n, or it is finite. Okay, then we say that it's at most countable. So that means every finite set is at most countable and every countable set is also at most countable. And finally, a set X is said to be uncountable if it is not at most countable. Okay, I am saying it is not at most countable. Yes, yeah, that's right. Not at most countable. We have to be careful with these definitions. One mistake and it's gone. You are saying about something else. So what is this final part? A set X is said to be uncountable if it is not at most countable. At most countable means what? Countable or finite. Not at most countable means negation of this. Okay, and negation of this is what? From your elementary logic, propositional logic, this statement or this expression is logically equivalent to this and, because we are considering negation, so or will become and negation of finite. That means an uncountable set is a set which is neither countable nor finite. That means it's an infinite set. Not finite means infinite. So it's an infinite set. An uncountable set is an infinite set which is also not countable. Okay, that means it's an infinite set which does not have a one-to-one correspondence with n. So let's just write that equivalent statement also. So X is uncountable if and only if it is infinite and not countable. Okay, so this is the notion of a countable set, an at most countable set, and an uncountable set. Now, finite sets, of course, we have many examples of finite sets. We have already obtained an example of an infinite set, which is the set of natural numbers itself. And according to this definition, the set of natural numbers itself is also countable because there is a bijection between n and n itself. Namely, there are in fact many bijections, in fact infinitely many bijections, but one particularly easy one is there, that is the identity map from n to n, which is both of course 1 to 1 and 1 to, so it's bijective. Okay, so let us now see where these notions lead us. Okay, so after having this definition, we immediately have a remark. Countably infinite sets are also called denumerable sets. And I have my own remark about this definition, which is that in some texts, whatever we are, this word countable, in some texts, by countable, the author means at most countable, and whatever we are calling countable, they call it countably infinite, specifically countably infinite. Okay, but here we are not adopting that terminology. For us, countably infinite and countable mean the same thing, that is having a one-to-one correspondence with the set of natural numbers. And at most countable means either the set is countable according to this definition or is finite. Okay, so that's the thing for us. Then we have an example. Yeah, so that's what the author is saying now, what I said just now. From the preceding discussion, we see that the set of natural numbers itself is a countable set. and so is this. Okay, but how? This is also countable, we are now saying. That's because we have already seen just now that there is a bijection between n and this. Now, by the definition that we have given for countability of sets, that means we have a bijection of this set with n, so that means this must also be countable or countably infinite, same thing. Another example, when these notions were introduced for the first time by Georg Cantor, there was a furor and in the mathematical community, and some people vehemently opposed these things. That is because these things I should not say had, but they have this counterintuitive property of having bijection with their proper subsets, which is something we do not generally see in finite sets. So mathematicians did not want to accept this notion at all, which greatly troubled Cantor. However, Hilbert in fact supported him. I am not sure whether Hilbert was Cantor's contemporary or not, but one of the mathematicians who opposed this notion is Henry Poincaré. But nowadays, of course, we do not have such a, dare I say, narrow-minded view of mathematics, where we just simply do not want to accept this thing for our personal biases. Nowadays, this is generally accepted, and we have these things in maths, and in fact, they are very important. So another example, in fact, Poincaré went so far as to call these things a disease in mathematics, but Hilbert countered by saying that this is a paradise from which no one will expel us. And yes, I also believe Hilbert. Another example of a countable set is the set of all even natural numbers. And the bijection here, in fact, how even natural numbers look, from that itself you can guess the bijection. The function, let me call this one also f. Given by this is a bijection. I leave the verification of this to you. It's an extremely straightforward thing to verify. Okay, so these are some examples of countable sets. Next, let X be a countable set. then in any countable set, then by definition, by the very definition of countability, there is a bijection between n and f. We are now going to use that bijection to express the elements of x in terms of that function, in terms of that bijection. Then by definition, there exists a bijection f from n to x. So informally, we can write the set x itself like this: f of 0, f of 1, f of 2, f of 3, and so on. It's like the function f has given us a way of what should I say, listing all the elements of x in a definite fashion, in a definite pattern. Of course, we will not be able to ever finish writing the complete list, because the numbers involved in this list are, the objects involved in this list are infinite in number. But still, we know what the next number could be. No matter how many we write and we say we stop at some stage, after that we know what is going to appear next in this list. So in that sense, we actually have expressed all the elements of x using the function f. The function f helps us label the elements of x. So there is a 0th element, a first element, a second element, a third element, and so on, so that you can arrange the elements of x in a sequence. All the terms of this sequence are distinct, and all the elements of x appear in this sequence precisely once. All these things have been written here. Should I write them down? Okay, let me just, because I am writing, so let me just write this one also. Thus, a countable set can be arranged in a sequence so that we have a 0th element, a first element, a second element, and so on. And is there anything else important the author has written in such a way that all these elements are distinct and together? Yeah, in such a way that all these elements are distinct and together they fill out all of X. The choice of these words is important. I just want to draw your attention to this. In such a way that all these elements are distinct, this distinctness stems from the one-to-one nature of the function f. That's why the images are distinct when the inputs are distinct. That's where the distinctness is coming from. And they together they fill out all of X. That stems from the onto nature of f. F is a surjective function. So whatever element X you can, whatever element in X you can think of, that is f of something. So in that sense they fill out all of X. And this is why we call this type of sets countable. This is why X is called countable. You can literally count the elements. It's a different matter, of course, that the counting will never stop, but it just goes like this. And if you are thinking of some hypothetical machine which can say actually count all the elements, then no element will be left out from this counting process. And also because of the distinctness, no element will be counted more than once. Every element will be counted exactly once. So this understanding lets us quickly see whether a given set is countable or not. That's because if you are able to actually list the elements of a given set in such a fashion, maintaining all these things, then of course you can guess that it will be countable. And for those sets where you struggle to list the elements in any particular order, so that you have ultimately you have all the elements, in the sense that you can just simply put ... after some time, and still you would know in your mind that yes, I know what appears in that part where I have not written the elements. If you struggle to do that for a set, then that's a sign that the set is not countable. So from the I need ink, just give me a moment. So from this point of view, it's easy to see why the natural numbers where you have the elements listed like this, the positive integers which is in fact this set, where also the elements can be listed like this, and the even natural numbers are countable. Because you see, in all of these sets we have written the sets in roster form, that is tabular form, where we list the elements separated by comma. We know that the things start at some point and then they follow a definite pattern, and once you get the pattern, actually you get everything. Okay, so here also we have that thing, here also we have that thing. So, and from these representations of these sets, you can immediately see what that bijective function is that the set needs to have with n in order to claim that it is countable. In this case, that bijective function is just the identity function, where 0 gets mapped onto 0, 1 onto 1, 2 onto 2, 3 onto 3. Here it's that function where n 0 gets mapped onto 1, 1 to 2, 2 to 3, and so on. Here 0 gets mapped onto 2, 0, 1 onto 2, 2 onto 4, 3 onto 6, 4 onto 8. However, it is not so clear if the integers from this point of view of representing a set in that pattern, from that point of view, it is not so clear if the integers or the rationals where I actually want to write what the author has written. It may look, the numbers may look random, but he has in fact chosen this number to show something about these sets or the reals. And here also he has written something specific. Zero square root of 2 minus pi 2.5 and so on are countable or not. we will answer these questions soon. So you can see that when you write the set of integers like this in roster form, of course here also you are listing the elements, and you have in fact in this way of writing things managed to capture the pattern. However, something is I mean it's not exactly like the previous things which are if you say just infinite, whereas in this list we think we see a doubly infinite thing. It's going indefinitely in this direction and also indefinitely in this direction. So what will you do? How will you set up the correspondence of this set with another set, namely the set of natural numbers which is singly infinite? Okay, so there you just stop a little bit. It's not as straightforward. And here the situation becomes even more complex when we think of the rational numbers. Now, this way of writing the set is actually a desperate attempt by someone to list the elements in the set of all, oh sorry, I say complex number, rational numbers. Okay, so if one wants to list the elements in the set of rational numbers in this fashion, they will just get overwhelmed, because what will you write? Say you have taken 0, then what will you write then? If you want to write a positive rational number, you then face the question of what the next positive rational number is. There is no such thing, we have already seen that. Unlike this here, for example, after 0 we know that 1 comes. Here however, that attempt led the author to write 1/4 say, but before 0 and after 0 and before 1/4 there are infinitely many rational numbers. How will you write them? Will you use ... If so, where? But there are negatives also. So you quickly realize that this type of writing is simply not possible here. Here it is somewhat possible using 2 ellipses, 2 instances of ellipses. Here however that's not possible. So it's a very poor way of writing the set of rational numbers, and when you go to reals things become absolutely the worst. Here besides having such densely packed rational numbers, you also have to deal with irrational numbers, and there are of course among them algebraic numbers and transcendental numbers. All types of things will come. So we quickly lose the ability to at least guess that the given set should be a countable set. So we will see which one among these 3 sets are countable, or something we perhaps already know, but we will show these things later on. So we will answer these things soon. Okay, now next, from proposition 3, 6, 12 and this is not 3, 6, 12, no, it's 3, 6, 4. 3, 6, 12 is a theorem, and theorem 3, 6, 12 we conclude that every countable set is infinite. However, we are not so sure whether the converse is true or not. Is every infinite set countable? It's a question. But what are we saying here? From proposition 364 and theorem 3612, we conclude that every countable set is infinite. Do we not already know that every countable set is infinite from the definition? No. You see, what the definition says is that a set X is called countable if there exists a bijection, so I am showing both ways, okay, between X and the set of natural numbers. That by itself immediately does not tell you that X must be infinite itself. As a set, X must be infinite. Okay, because you see, the definition of countability does not explicitly say also additionally that X has to be infinite. It just does not say that. It just simply says that there should be a bijection between X and N. But where does the infinite nature of X come from this? That comes from theorem 3612, where we showed that N is infinite, and proposition 364, which says that this sets having equal cardinality, this relation is an equivalence relation, that it is reflexive, symmetric and transitive. But how does it follow from these things that X is infinite? Say X is not infinite, okay, say X is finite, then by the definition of finite sets, X would then have a bijection with a set like this for some natural number N. Okay, so that just comes from our supposition that X is finite and the definition of finiteness. But then by proposition 364, because this is a bijection and this is a bijection, you can consider their composition to have a bijection between N and this set, which would then, by the definition of finiteness, tell us that N is itself finite, and that would contradict this fact that it is in fact infinite. So that's why our supposition that X is finite is wrong. X must be infinite. So that's how from these two things it follows that every countable set must be an infinite set as well. But what about the converse? The converse we don't yet know. Okay, we will see what the converse, what is the status of the converse. The converse is actually false. Every infinite set is not countable. However, it's not immediately clear whether every infinite set is countable. This also we will answer in this section itself. Note one thing, that right now I just simply mentioned that this converse is not true. However, we are still somewhat far away from showing that. So at this stage we don't know. Now if it turns out, which is not true, but still I am just saying for the sake of argument, if it turns out that every infinite set is in fact countable, then the definition of uncountable sets that we have given becomes vacuous. There would then be no uncountable set. But that is not true, which you already probably know. So now, before diving into the theory, which of course we are not going to do in this video, we need an elementary result about all these things. Okay, and that result is the well-ordering principle. So we are just going to see the statement, the proof anyway will be done in one of the exercises. It's a property of the infinite set of natural numbers which is very important. Let X be a non-empty subset of the set of natural numbers. That means the elements in X are natural numbers, may not be all the natural numbers but some, and X is non-empty. There is at least one natural number in X. Then there exists exactly one element n in X such that n is less than or equal to m for every element m in X. That is every non-empty subset of n has the smallest element, which is something that is easy to believe also. However, we will prove this in one of the exercises from things we already know. Specifically, we are going to use the principle of mathematical induction to prove this. But there is another fact about this thing, the relationship between well-ordering principle and the principle of mathematical induction, that perhaps I should say. It's not just simply the fact that the well-ordering principle is a consequence of the principle of mathematical induction, but the converse is also true. If you assume the well-ordering principle to be something given and true, then from this you can also prove the principle of mathematical induction. So these two statements, the well-ordering principle and the induction principle, are actually logically equivalent. Any one of them can be chosen as your axiom, and the other then becomes a theorem or a result. So we will prove this in I have not written here which exercise. I think it will be proved in exercise 8.1.2, the second one. We will see when we deal with the exercises. So that's just it. So I end things here itself. Next week we will see what comes next. Next week we will start actually proving things. So that's it for tonight. If you want to say something about these things, you can use the comment section or you can mail me at my address. The link will be there in the description. Okay, so the next video is on Tuesday, and we have already gone through what? Herstein's algebra. So let's do field theory on Tuesday. Okay, so with that I wrap things up. So see you on Tuesday. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.